We're going to simplify some radicals, starting with square root of 99. Yes, we're live again. You are live. Yay. Say hi to the world. Yay, cool. Thank you. The nice thing about radicals, like I mentioned earlier, is that you can break them up into a product. So let's think of a couple things you can multiply together to get 99. 9 and 11. What's special about the square root of 9? It's a perfect square. Good. And so the square root of 9 is 3. So you simplified this radical. We got rid of the perfect square that was buried deep inside here. So that's nice. Now, we're going to play the same game with 72. And for the benefit of my viewing audience here, let's do this. 1 squared, 2 squared, 4, 3 squared, 16, 25, 36, 49, 64, 81, and 100. So basically listing out all the perfect squares. If we played the same game again, what numbers occur to you? 9 and 8. That's the long way. So my suggestion would be to work with this number, 72, fits in between these two, and work your way up. Does 64 go into 72 evenly? No. How about 49? Does that go in there evenly? No. How about 36? 36 goes in there twice. So then that becomes 6 times the square root of 2. Done. Nice and fast. Now, you could have got there if you did it the other way. This just would take you longer. So let me get another sheet of paper here. If I did this as square root of 9 times square root of 8, say, okay, well, that's 3 times the square root of 8. But then the square root of 8 breaks up as the square root of 4 times the square root of 2, which is 3 times 2. And wow, that feels like a lot more work doing it that way. I mean, you'll eventually get to the right answer, but yuck. So the trick is to find the largest perfect square that evenly divides your number. That works out great as long as you're doing perfect squares. What if you're doing some work with cube roots? Well, we can play the same game with cube roots. Let me test myself on my cubes. So 1 cubed is 1, 2 cubed is 8, 27, 64, 125, 216, let's see, 6, 7 would be what, 343, 512, and 729, 1000. There we go. So there's your list of perfect cubes. So what if, and this is one of the problems that was in Newton, they gave you the cube root of 448. Now, instead of using this list, we're going to use this list. 448 is right here. Work your way up the list and try and find the largest perfect cube that goes into this evenly. So, yeah, if you do 448 divided by 343, it's not going to go in evenly. It's not an integer. And you keep going. 448 divided by 216, nope, doesn't work there. By 125. And finally, you get up to 64, bingo, and it works evenly. So you're working your way up the list. So I'll write that as a cube root of 64 times a cube root of 7. Why does that help me out? What's the cube root of 64? 4. 4 cubed is 64. So that's 4 times the cube root of 7. Yay! Let's do another couple from this one, or from this set. For example, What if I had the square root of 9m squared? That one's not so bad. Square root of 9, square root of m squared. Square root of 9, I hope you don't need your calculator for that one. Square root of m squared is m. And we're actually going to have to come back and adjust that one a little bit. That one's not quite perfect yet. Why not? What's wrong with that one? Well, let me come over here to the side. And you don't have to copy this down, just try and understand the point of this. Let me start out with the square root of 5 squared. Now 5 squared is 25, the square root of which is 5. Okay, nothing terribly exciting there. If I started out with negative 5, same thing, right? The problem is, when I have a variable, I don't know if it's starting out positive or negative. But I do know that it has to end up as positive. I have to guarantee that this term here is positive. So what guarantees that that term is positive? And I'm trying to like throw it into your brain. All right. Now, if you're at home listening to the video, you can't see it, but I'm not signaling touchdown. Absolute value. Yeah. Thanks, Joe. Yeah. So you need the absolute value around this is what you're going to need, because that's going to guarantee that this thing is positive. So the little piece that I was missing here, and it's annoying, but we need it, is the absolute value. You have to have the absolute value around those terms like this. So a good question is like, well, all right, just tell me when I need the absolute value, because you're not always going to need it. And it gets a little bit tricky to say in general. This is where I wish I had a little bit more control over Newton about the exact kinds of problems that you get, because I would avoid some of these. But if you have an even root of, whatever, that results in an expression to an odd power. So an even root that says something to an odd power, that's when you're going to need the absolute value. So I'm going to give you a couple examples of stuff like this. Let's take a look at the square root of y to the 10th. Square root of y to the 10th, that's an even root, and y to the 10th. Well, there's a little bit of a trick here. You can take this exponent and divide it by the index. 10 divided by 2 gives you 5. Looks pretty good. Except because 5 is odd, you would need the absolute value. Let me do a different one. Cube root of x to the 12th. Same kind of game here. Let's divide the exponent by the power of the radical. 12 divided by 3 is 4. Is 4 odd? No. So you don't need the absolute value. The other reason you might not need it is because this power out in front of the radical is odd. Only have to worry about it if you have an even powered for the index of the radical. Let's try a couple more here. What about the 6th root of x to the 30th power? Okay. Play your rule for exponents. 30 divided by the index of the radical, 30 divided by 6 gives me x to the 5th. Do I need the absolute values around this one? Yes, because I've got an odd exponent and an even index of the radical. So I need it around this one. Let me give you a couple more for you to chew on. So let's see, let's do the 4th root of a to the 20th power and the 5th root of, let's see, let's do c to the 35th power. See what you can come up with for those. Try and decide if you're going to need the absolute value. Yeah, me too. So let's take a look at the first one. Angela, I'll get a to what power here? A to the 5th. Do I need the absolute value on this one? Yes. Well done. All right. Need the absolute value there because this is even and that's odd. You're going to need the absolute value. How about over here? C to the 7th. The index of the radical is odd, so you don't need to worry about it for an odd radical. You do for an even powered one, but not an odd one. So subtle difference there. I hope this is something you kind of catch on to because Newton will mark you wrong if you forget these absolute values, and it's really annoying. It happened to me, and at first I'm like, oh, wait a minute, there's a mistake here. And then I'm like, oh, okay, they expect us to do the absolute value thing. Got it. All right. So at least you're getting a little heads up so that you won't get set backwards in your work on this. Along with that, let's take a quick look at something like this. 4th root of -1. What could you raise to the 4th power to get -1? Could -1 work? -1 to the 4th power? Well, let's see. That'd be -1 times -1 times -1 times -1. What's the product of 4 negatives going to equal? Yeah, it's going to be a positive, so a +1. So there's nothing that's a real number that'll work here. So again, this is not a real number, right? Narn. Yeah, extra credit there, right? Narn. Good job. And typically you're going to get narn if you have an even root of a negative number.
So it's okay if we make our answer a narn?
For now. Eventually we're going to learn what these things are, which is imaginary numbers. And they're not really imaginary, it's just what they're called because when they were first created, invented, discovered, people didn't like them. So they said, this is ridiculous, it's imaginary. And the name stuck. So that's why they're called imaginary numbers, even though you need imaginary numbers when you're studying such real-world things like electronics and physics. So they're part of the fabric of our world. Yeah. I mean, there's a lot of applications for those things. Let's do a couple more here. Let's see. Cube root of -128. So let me begin by going back here, looking at my list of perfect cubes. 128 is right here. Work your way up that list. Is there a perfect cube that divides 128? 64. Good. I'll also put the negative out in front here. So -64, cube root of that, and that's going to leave behind a 2. What's the cube root of -64? Thanks, August. -4. So negative 4 times the cube root of 2. Square root of 156. Let's do z to the z to the 18. Now this one's kind of a pain. What list am I going to look at? Perfect squares or perfect cubes? Perfect squares. And you can march all the way up your list, and the largest perfect square that goes into this evenly is going to be a 4. Ugh. So I'll rewrite this as a 4. 4 times 39 is going to give me 156. Z to the 18th, that's going to go here, because that's a nice perfect square. Z to the 18th is divisible by this number out in front of the radical. What number is that understood to be, even though I didn't write it? 2. 18 divided by 2, hey, we're in good shape. So that'll be 2. Z to what power? Z to the 9th times the square root of 39. And if you put this in on Newton, it's going to mark you wrong. After all that work, it's going to mark you wrong. How rude. Why? What's missing? Ooh, bingo. Way to go. Absolute value. This is even, and that's odd. So you need the absolute value on that one. The power of the radical was even, and the power of the variable when we ended up was odd. So yeah, watch out for that one. It'll catch you. Now we did one like this earlier. Let's see, where we had the 6th root of y to the 30th was y to the 5th, and we needed the absolute value there. What was nice about that one is that it worked out even. But what if instead of y to the 30th, what if I had y to the 32nd? 6 doesn't go in here evenly, does it? Georgie?
Before we move any further,
Yeah.
absolute values y.
Because this is even and that one's odd.
I thought you said if the number that you're recruiting by is
This would have to be even,
yeah.
and that has to be odd. I hope I've been consistent on that. Am I wrong?
We did
Okay.
we did one where it was 6, and then we got absolute value x5.
Yeah, which is pretty much the exact same thing here. Okay. Now, the problem that we have here is that 6 doesn't go into this evenly. So here's what we'll do. We'll take advantage of the fact, and I think you were humming something about this earlier, 32, y to the 32 is really y to the 30th times y to the 2nd, right? When you multiply things with the same base, you add their exponents. So I'll rewrite this as the 6th root of y to the 30th times the 6th root of y to the 2nd. Okay. Well, at least I can do something with that radical out in front now. That's going to become y to the 5th, y squared. And let's not get this one wrong. What else do I need? Absolute value. Sorry to do that to you, but they're going to expect that. All right. Let me give you one more like this. Let's do, say, the 4th root of, let's do a to the 21st power. Fourth root of a to the 21st power. Now, kind of like the last one, I want this exponent to be divisible by this, right? 21 to be divisible by 4, but 21 is not divisible by 4. Is there a number close to 21 that is divisible by 4? 20. How many would that leave left over for this one? 1. And this is still the fourth root. Let me squeeze it in here. 4 and 4. See if you can't finish that one up. Well done. So 20 divided by 4 is a to the 5th power. Because that was even and this is odd, we need an absolute value. Absolute value of the fourth root of a. Bravo. Thank you.
Or like just technically like wrote down the same thing. Like fourth root and
Oh, if you put a 1 here?
yeah, it's same.
Oh, if you put a 1 here, that's fine. That's not a big deal. Yeah, the reason I put the 1 here is to make sure it was clear that we had them all accounted for. It should. If it doesn't, if Newton wouldn't count something like this, then send them a little feedback. Send them a little nastygram. Say, hey, what up? Because that would be right. I would count it. So that's really all that you need to worry about is that I would count it. Anything else on that one? All right, cool.